Network programmers use hashing extensively, but often compromise security for performance, leaving their applications vulnerable to attack. In this talk, I'm going to present the work my colleague Jiaqi Chen and I have done on implementing a secure and efficient hash function that runs directly in the data plane. Today's data plane is the backdrop of an immense struggle, a struggle between sophisticated network applications and implementation challenges that network programmers encounter when they try to fit these applications efficiently onto network hardware. As we know, in recent years, network switches have become increasingly more programmable and intelligent, enabling deeper packet-level programmability and fine-grained control. This unprecedented insight into and control over the network enabled by deep programmability has provided programmers the opportunity to build exciting new applications for improved in-network security, privacy, performance, and reliability. Unfortunately, these more sophisticated applications are often bottlenecked by hardware limitations and constraints, the other piece of the network landscape tug of war. In order to offer applications that are high-speed, robust, and useful for dealing with heavy traffic, especially in an adversarial case, it's highly desirable to fit applications into network hardware like the Tofino switch, enabling them to run directly in the network. So programmable switches have become increasingly more powerful and capable in recent years. But even so, strict constraints like the limited arithmetic operations available and the limited number of pipeline stages on the switches makes implementing sophisticated applications in the network still quite challenging. Of the applications in this evolving network landscape, many of them use hashing extensively. The purpose of a hash is to take some input, do some amount of processing, and then spit out a random output, which an attacker could not themselves generate without insider knowledge of keys in the original input. A few of the ways that hashing is used in the network include indexing, for example, hashing the header fields of a packet to use as an array index for a table, fingerprinting, using a hash to fingerprint a longer flow ID into a shorter one, and random sampling, using a hash of network traffic along with some type of threshold to select a random subset of the traffic in the network. A few examples of recent network applications that use hashing in these three different ways include Jockin and Netcache for indexing, Silk Road NP4 RTT for fingerprinting, and Aroma and Boku for sampling. So we see that hashing is an important way of collecting, storing, and managing network information. Network hashing is most often conducted using CRC32, which is a cyclic redundancy check and error detecting code. CRC32 is ideal for network use in the sense that it's quite efficient. It is computationally inexpensive and it's fast, both of which make it a popular choice for in-network applications that would like to conduct as close to line rate hashing as possible. CRC was originally designed to take an input, generate a checksum, and then perform verification on that checksum by comparing the checksum received with a freshly generated checksum, returning either a 0 if the checksum were correct and unchanged from the original, or a non-zero value if the checksum were incorrect and had somehow been polluted. In other words, CRC was designed to catch accidental bit flips in a communication channel and non-intentional changes. Because of this, CRC is insecure in the sense that it's not robust to an adversary who might specifically design an input to generate a certain checksum. And even if some type of key or secret starting CRC value were used, the adversary could still manipulate the input to get their desired output by figuring out a mapping between specific inputs and outputs. So when CRC is used as a network hash, it has severe limitations stemming from its inherent design. It's not a cryptographic function, and thus quite simply, it's insecure when it's used as a hash. CRC's weak hashing properties cause unintended behaviors and allow adversaries to exploit security loopholes. For indexing, an adversary can manipulate the CRC checksum to force table updates and evictions to go to the same index. Similarly, for fingerprinting applications, a network attacker can cause collisions that will inaccurately group flow IDs together with the same fingerprint, leading to incorrect network processing. In a sampling scenario, an adversary can construct hashes such that some traffic is never sampled, thereby bypassing monitoring, or always sampled, causing a system overload. Given the heavy reliance of many applications on hashing in order to accurately measure, collect, sample, store, and divide network traffic, it's important for the hashing building blocks to be secure and not easily tampered with. So, we need a more secure hash as a building block for reliable and correctly functioning applications. Do these exist? Yes, they do. A few examples of secure hashing functions include SHA-256, scrypt, and blowfish. Unfortunately, however, things are not this simple. Secure hashes are computationally expensive to implement in network hardware and have complex implementation needs that are unfriendly to the data plane, causing inefficiencies and unacceptable slowdowns to the application. Due to all of this, network programmers have historically been forced to choose CRC32 as their go-to hashing function, compromising security for lower computational cost and implementation simplicity. So on a spectrum of security and speed, on the left side, we have the quite secure hash functions SHA-256, scrypt, and blowfish, which unfortunately are not fast. On the right side, we have checksums and CRC32, which are fast and efficient, but sadly not secure. So into this landscape, we present SipiD, HalfSipHash in the data plane, which provides a good balance between both security and speed. We're going to discuss in just a moment what HalfSipHash is and how we implemented HalfSipHash for the data plane. But before that, I want to explain really briefly why SipiD shows up on the spectrum a little closer to security and a little further away from speed. SipiD requires multiple iterative rounds of processing for every single input that it receives. And because of this, it ends up taking a little more time and being slower than hashes or checksums like CRC32, but it does provide security. So it shows up a little closer to security than speed on our spectrum. So HalfSipHash is from the SipHash family, which was designed by Jean-Philippe Amasson and Daniel J. Bernstein. It was designed to be a fast keyed hash specifically for short inputs. Now, the variables CD at the end of HalfSipHash specify the number of compression and finalization rounds for the hash, respectively, where each 4-byte input word to the hash gets processed by C compression rounds, and then the total input undergoes an additional D finalization rounds at the end of all the processing. So let me briefly walk through what HalfSipHash-c-d looks like on an 8-byte input. So what we'll see is there's some amount of pre-processing that occurs with keys and internal variables V0 through V3. And then each 4-byte word of the message is going to get processed by 2 compression rounds. 2 because HalfSipHash-c-d specifies C equals 2. So the first 4-byte word is processed by 2 compression rounds. And then the second 4-byte word in our 8-byte input is processed by an additional 2 compression rounds. Finally, there's 4 finalization rounds at the end, and that's how you get your output. Looking really quickly underneath the hood of these compression and finalization rounds, we actually see that both types of rounds have the identical operations. They're only named differently because of the roles that they're fulfilling. So something I'd like to draw attention to for the operations in a single HalfSipHash round is that there are 14 of them, a good number of operations to perform per round. Additionally, we see that we have 6 circular bit shifts for each round. And in the next slide, I'm going to explain that if implemented naively, these circular bit shifts can end up taking too many stages, or what are called pipeline stages, in our switch, and this will end up becoming computationally expensive. So at a high level, something to understand here is that each HalfSipHash round is expensive in its own right in terms of the number of operations and circular bit shifts. But as we can see on the right side, we have to do these individual half-SipHash rounds multiple times, 2 additional rounds for every single additional 4-byte word in our input, and then 4 finalization rounds at the end. So there's a good amount of processing that has to be done. Now, the good news is that we now have this secure hash, but what we still have to do is figure out how to implement in the data plane efficiently enough that it will not be too slow to implement in our applications. As we began to tackle this challenge, we ran into a few limitations, which we've discussed very briefly before. The first constraint that we ran into was the limited number of arithmetic operations available on a network switch. So a few operations that are available on a network switch include addition, bitwise XORing, and similar operations. The switch, however, is unable to perform operations like division, and additionally, network hardware does not natively support circular bit shifts. And we saw in the previous slide that even a single round of our SipHash, half-SipHash, is going to require 6 circular bit shifts. So since network hardware does not natively support circular bit shifts, a naive approach to implementing circular bit shifts would be something like the equation on the right here, where you have an input and it gets shifted to the left and then shifted to the right again, and then bitwise ORed. This unfortunately requires intermediate steps and ends up taking too much computational processing time. Let's walk through a quick example of what this type of approach would look like. So say n is equal to 5 in this example, and we have an 8-bit word A. Excuse me, an 8-bit string A, 8-bit input. So we would like to shift A circularly to the left by 5 bits. Our result should be, as you can see, the lower 3 bits of A end up showing up at the top, and then the upper 5 bits of the original input are going to wrap around to the bottom. Unfortunately, however, there are these intermediate steps that have to be performed. First, A has to be shifted regularly without any circular shifting to the left by 5 bits. And if you notice, the lower 5 bits are now padded with zeros. And then you're going to shift the original input A to the right by 8 minus 5 bits, where 8 is the size of your original input. And so now you see the upper 5 bits are shifted down, and then the 3 bits at the top, the most significant 3 bits, are now padded with zeros. Finally, you can now take X and Y and bitwise OR them together in order to arrive at your final result, which was the circular left shift by 5 bits. So as we see here, this approach is going to require 3 operations, these intermediate steps, and a bitwise OR. Now, because of ALU dependencies between the shifting and the bitwise OR, this is actually going to require at minimum 2 stages, 2 pipeline stages in the network switch. This is going to become computationally expensive, especially since we have so many of these circular bit shifts to implement. So instead of this approach, we came up with a semantically equivalent slicing mechanism that, instead of doing all these intermediate steps, simply slices out the bits that we desire from the upper and lower parts of our original input, and then concatenates the 2 sets of bits together, storing them in a new variable. So it looks something like this. Say n is equal to 5, and again, we want to shift A over by 5 bits circularly. Say A this time is a 32-bit input. What we'll have is you'll slice out the lower 27 bits from index 0 to 26 of A, and then put that at the top, and then slice out the upper 5 bits from index 27 to 31 and concatenate that at the bottom. And this achieves your circular wrapping around. So now what you have, instead of a left shift, a right shift, a bitwise OR with 3 operations across 2 pipeline stages, you simply have slicing out some bits and copying them over to a new variable. And this allows us to now perform the entire process in a single operation, and very importantly, a single pipeline stage. And so now we've figured out how to do this in the most efficient manner possible. So Now we can implement each operation in a single stage, even circular bit shifts. But the next challenge that we had to grapple with was the limited number of pipeline stages that are available on a network switch. So here again, we see the original HalfSipHash round, which has 14 operations and 6 of them are the circular bit shifts. Thankfully, we figured out how to do the circular bit shifts in an efficient manner, but now we want to see how we can fit as many of these operations into as few stages as possible. Now remember, the reason why we're doing all of this is now we have the secure hash, we have HalfSipHash, but if we don't figure out how to put this onto network hardware as efficiently as possible, we might end up being computationally unaffordable, and that will make our application less desirable for network programmers to implement. So in addition to the limited pipeline stages, we have some related constraints that we had to grapple with. Typical hardware pipelines have multiple ALUs or arithmetic logic units per stage, but any operation that has dependencies has to occur in a different stage. In fact, operations can only be performed concurrently if they are entirely dependency-free. Another constraint we had to deal with was the limited memory available in network hardware, which constrained how many active variables we could have in memory at any given time. So our goal was to deal with all of these constraints, deal with the challenges, and find the optimal grouping of dependencies for these operations to fit it concurrently into as few stages as possible. Now, using some variable renaming and making sure we were following the dependency constraints very closely without at all violating any dependency constraints, we were able to come up with the following groupings, fitting all 14 operations and ensuring that they would execute within exactly 4 pipeline stages on our network hardware. So now we have figured out how to implement our operations in as few stages as possible and fit a SIP round in as few stages as possible. As we saw previously, however, it's not good enough to just have a single SIP round. We have to do multiple iterations of SIP round processing to do an entire HalfSipHash. Now, as we see in this visual here, we are able to fit a SIP round into 4 stages. And this picture is of a pipeline where we see we have 2 SIP rounds fit into a single pipeline pass. And then you have a few additional stages at the beginning and end of your pipeline for setup and teardown processing. So to implement multiple SIP rounds, we first tried to fit as many SIP rounds as possible into a single pipeline pass. After that, we used both the ingress and the egress pipelines to perform more processing. And finally, we used the concept of recirculation to get the additional SIP round processing in. So this equation here shows the number of passes through a pipeline, through a single ingress-only pipeline, that are required to process an M-byte input to SipiD. Let's walk through a quick example of what this might look like. Say M is equal to 16 bytes. We know C to be equal to 2 based on the number of compression rounds per 4-byte word, and D is equal to 4. K is given by the number of SIP rounds that we can fit into a single pipeline pass. And as we can see from the visual below, K is equal to 2. We can fit 2 SIP rounds per single pipeline pass. Plugging all these numbers in, we find that P is equal to 6, or we would require 6 passes through a single pipeline in order to process a 16-byte input to HalfSipHash. So using an ingress-only version, this would mean that we have to recirculate our packet 5 times in order to get all 6 passes done for a 16-byte input. If you would like to reduce this overhead, you can use both ingress plus egress pipelines, which would reduce the number of passes required to 3, and subsequently reduce the number of recirculations to 2 for a 16-byte input. We implemented our design in hardware. For our ingress-only version, we implemented our design in 490 lines of P4 code. And for ingress plus egress version, we implemented it in 779 lines of P4 code. And we ran our design on a barefoot Tofino wedge. In terms of hardware resource utilization, we saw that we had quite low resource usage, particularly in terms of memory. Most of our resources went towards hash units and towards packet header vectors. We note that in particular for hash units, these are normally used in network switches for CRC32. But for applications using SipiD, you would not require CRC32 and thus would not need these hash units. In particular, we want to note that since our program is not memory intensive and uses such little memory, it can easily coexist with other applications. And in particular, it can coexist with memory intensive data plane applications such as network measurement and telemetry applications. Our implementation of SipiD has an application dependent overhead. So we saw that there is a good amount of iterative processing that has to occur. And in particular, for each additional 4-byte word in an M-word input, we're going to see additional processing. Fortunately for us, however, network applications typically require quite short inputs to their hashes. And this is because oftentimes they're just choosing certain fields in the header of a packet and hashing over that. You would typically never see a hash over an entire packet or over an entire packet payload. So that's great. And we can see from this table here, a number of the network applications that I mentioned previously, the input sizes that each of these applications are currently using. And these applications are using CRC32, which we saw was insecure. But what we do notice is that most of these input sizes are rather small. So another thing to note is that because of the amount of processing and the number of SipRounds that we have to do, inevitably we do have to do recirculation, although this number can be smaller for smaller inputs and if you use both ingress plus egress pipelines for processing. A question does arise though, how do we know whether it's acceptable to be below line rate for your hashing? A few things to note is that not all ports on your network switch might be serving adversarial traffic, and thus you might only need to do processing on, for example, internet-facing ports where you expect potential adversarial packets. You might imagine that for packets and ports on the secure side of the network, that is the internally facing side of the network, you might want to instead use a faster and potentially less secure hash. Additionally, not all packets in your network might need hashing. For example, only handshake packets might need SipiD. And then another thing to think is that you might want to dedicate recirculation ports and think of this as the cost that goes into ensuring secure hashing is done on your network. So in terms of evaluation, we show here in this figure that we can perform over 300 million hashes per second for an 8-byte input. And we show also the results for 16-byte, 24-byte, and 32-byte input in terms of millions of hashes per second. We especially note that our 16-byte input performs 150 million hashes per second. And for example, an application like Netcache, which quickly handles queries and performs load balancing, it's currently using CRC32 with a 16-byte input, but it could transition to using SipiD instead, and for that same 16-byte input, be able to do 150 million hashes per second and do so securely. We also saw in our evaluation that our ingress plus egress design performed for a maximum hash rate over 3 times faster than our ingress only design. And for a 16-byte input on ingress plus egress, we saw an approximately 5 times speed up over a single core CPU. Another thing I'd like to note is that all these results are for a default 100 gigabytes per second reserved recirculation throughput per pipeline. But if you would like to increase this and get a higher hashing rate, you could reduce your forwarding throughput and increase your recirculation throughput, making this trade-off as aggressive as you need. And this might be desirable for applications that require faster data plane hashing. So now to conclude, we saw that in-network applications rely on hashing extensively and unfortunately use CRC32, which is insecure. We would like both speed and security in our network applications, so we present SipiD, HalfSipHash in the data plane. Our design is available at the following GitHub link. And you can also search up SipHash Tofino and find our GitHub repo this way. For future work, we're looking at how to integrate SipiD in network applications ourselves and would encourage other network researchers and programmers to begin thinking the same thing and trying to migrate from the fast but very insecure CRC32 towards the more secure and still efficient SipiD. Thank you very much, and I'd be happy to take any questions now.